got a stack here, so please go ahead and take one if you don't have one already, right? So twice a year we publish the JWST Pocket Guide, usually in time for the AAS. There will be a new version of this for the winter AAS, but this one from the summer AAS is still pretty good. So nothing wrong with it. And that contains the throughput curves and the sensitivities with tables and wavelength ranges for all the instruments. Each instrument has a little fold-out area here. So we have MIRI, NIRIS, and you also have the science timeline here with the deadline in case you forget. So please take one. All right. So the exposure time calculator. So this presentation is not meant to be a sort of a hands-on session. It's not meant to show you how you use the tool. That's what we have the level 2s for later in the week, where you go through all the different science cases, instrument modes, and using the ETC is spread out in all those different sessions. The point of this plenary here is to tell you a little bit more about why we did the ETC the way we did it and how it works underneath the hood. And the reason we're doing that as a master class is not something we necessarily would do in a regular workshop, but the reason we do it now is that because you might get questions about that. Why is ETC doing this weird thing? Usually there's a reason for that. And hopefully we can help you with that with this presentation. As with the other talks, please interrupt, ask me questions along the way. We have ample time before lunch to do this. All right. So the presentation here, I'll go through all these different items here. I'll start with the history and design philosophy behind the JWST exposure time calculator. I'll go through the basic algorithm and the architecture and why it was done that way. We'll talk about strategies, which is a well-defined term in ETC land. This is an important one. I'll talk about the detector readout and how it's related to noise, because this is one of the things we get a lot of questions on. And it's very closely related to the ETC. And it's also related to the workflow that you typically will go through when you prepare a proposal. We'll talk about the reference database. This might be useful to you as well, because it's available to you. So there's a lot of reference data about the whole observatory embedded within the exposure time calculator. Scenes and sources, how you set up your astrophysical scene, and why it's the way it's done. Another important item here is the JWST background. The background for JWST varies tremendously with wavelength. It just has different components, and there's a fairly detailed model behind the whole thing that is an important input to the exposure time calculator. There's a little section here about special effects, so that's there's a lot of effects that are included in the ETC, such as what you do with cosmic rays, for example, what you do with correlated noise, and so on. Then there's I'll talk a little bit about how the exposure time calculator was tested, right? So how well can you trust the results that it provides? A couple of use examples. We'll discuss the collaborative features in the ETC, and in the ways that is related to the underlying algorithm of the engine itself. And finally, I'll talk a little bit about what we call the Pangaea engine, which is a Python module that runs the ETC. So it's something you can download and run with a Python script yourself, say in case you want to do a big parameter exploration using the ETC. All right, so first things first. You should know this from the homework here, but of course you find the exposure time calculator at this web URL. So there's not so much to say about that. It's currently at version 1.5, and this is actually the flight version of the exposure time calculator. So it'll be that you'll be using to do your proposals with. There's a number of different options here, and in the top level here, you can use for folks who are very unfamiliar with the ETC, we recommend that you use the quick start with kind of a wizard that takes you through the different steps of the ETC. But otherwise, you'd usually log in. Logging in means that the exposure time calculator will save your work, so that next time you log in, it'll be available for you there. If you want something quick and dirty, you can work anonymously. But once you leave the exposure time calculator, your work might not be there anymore. All right, some history behind this. Well, So this goes back a few years here, and you can blame me for some of this. We were looking at how are we going to support the web with an exposure time calculator, and what we had at that time was the Hubble exposure time calculators, and so those are split up into different instruments, and so you go to different places depending on which instrument you're at. And basically, for anybody who's been doing Hubble observations, and this is typical for many other exposure time calculators for other observatories. You fill out this web form, you press go, and it'll give you either your signal to noise given an exposure time, it'll give you an exposure time within an input signal to noise ratio. And then typically, filling out this whole form is then, you write down the result, and then next time you come back and use the exposure time calculator, you typically will fill out the form again. It's not quite true for Hubble. In this case, it can also give you a little code that you can write down in your notebook, and so next time you type in this little code, and it'll pop up your calculation that's pre-filled with however you filled it before, but you still have to keep track of things with on your own with your personal notebook. Another thing about the Hubble ETC is that it's a one-dimensional ETC to a large extent, and so that gives you certain limitations for what you can model. And we realized with JWST we have all these complicated observing modes, including things like IFU spectroscopy, slitless spectroscopy, coronagraphy, aperture masking interferometry, and so on. If we were to write a different one-dimensional exposure time calculator for each of these, not only would we'll have a lot of be a lot of code that is duplicated, but also a lot of code that is special, that's hard-coded for the different modes. But also it'd be difficult to model the noise, like say of an integral field unit type of instrument, if you abstract out all the multiple dimensions. And then finally, there is the JWST detectors. These infrared detectors operate differently than what detectors operate in the optical. If you have a CCD detector in the optical, a lot of you are probably familiar with that. You expose your pixels with light, it generates electrons, and when you read out the electrons with a CCD, what you basically are doing is you're moving the electrons out to a registrar on the side of the detector, and you're losing your electrons. You have one chance to read them. With the infrared detectors that JWST is using and that are used many other places, the readout sits underneath every pixel, and so what that means is that you don't have to move the electrons. When you read out, you don't destroy the electrons that are sitting that have been generated by your exposure. You can read it as many times as you like, and so that allows you to read out the detector while it's exposing, and so that has big advantages, and in particular has big advantages for JWST. But in order to model that, we had to do something else than using the HST exposure time calculator. So we needed something more modern. So back in 2012 here, this is. So we created a prototype exposure time calculator that included a lot of these ideas. So, because for one thing, it was a three-dimensional calculation where you have a what that means is you create a three-dimensional astrophysical cube, right? So you have two spatial dimensions and one wavelength dimension, and then you project this down on a detector. So the detector has two dimensions, but it might encode three-dimensional information, right? So for example, if you have a slitless spectrum, it encodes both spatial information as well as spectral information on the detector. So it could do that, and you would use model point spread functions, all these sort of things. The code for this could use then the same code for all the different JWST modes. And it was just a matter of, you make your cube. If you have an image, you project the cube onto your detector in a certain way. If you have a spectrum, you project it in a different way. But essentially, it uses the same code. And so you could have a scene, and you could view that scene with all the different observing modes. So here we have near cam and near spec. And so if you're doing, say, a near cam pre-image, when you create a scene for that, you calculate what the near cam pre-image would look like. And then you want to do a near spec multi-object spectroscopy. All you have to do is to make an ETC calculation of that same scene. You don't have to recreate your scene for another calculation. So this was in there, right? And so you could make a list of different calculations, and then you could compare them within the same tool. It was template-based, right? So this is similar to APT. So basically what that means is you have a mode. Every mode has a form that you fill out that's specific to that mode. And so you can see that on the right-hand side as well. All right, so based on this prototype, we made a number of recommendations for the development of the actual production exposure time calculator. All right, so for the first one here is that the ETC should use a 3-dimensional framework, 2 spatial and 1 spectral. The second one was that the ETC should use a point spread function library, and we had that very nicely because already in those days we could generate that with the WebPSF tool, and so this is also a public tool you can download and use it to generate your own model WebPSF or model JWST point spread functions. The third one is that in calculating noise, we should include correlated noise. And the reason we did that was that this is a sort of an issue with near-infrared detectors, particularly with the Mercat tail detectors that are used in the near-infrared instruments, NearCam, NearSpec, and NearIS. The read noise is correlated. And what does it mean? It means that the noise signal in one pixel depends on the noise signal in another pixel. You see this if you look at the raw frames, is that there's sort of striping across in the for the read noise. Now, there are ways to mitigate that with the readout detection. There's been a lot of work dealing with that before the data actually becomes available using different readout modes, but still, there's correlations in there. And so we wanted the ETC to be able to handle that so that every pixel is not independent of the other in terms of its noise properties. And we'll get back to that a little bit. We wanted to be able to have post-observation additions of multiple exposures, subtraction of backgrounds, extraction of photometry, and spectroscopy, and so on. And so this was important because how you subtract your background from your observation it affects what your noise is going to be. Right? So the more area you have to subtract background, the less noise this background subtraction imparts on your final signal to noise. If you're doing IFU spectroscopy, you're often doing a nod and subtracting the two from each other, or multiple nods. And so this is something that involves not just one exposure, looking at the same point in the sky. You may do an exposure and then you offset it a bit, you do another exposure, and then you have some sort of arithmetic operation on those two before you get to your final signal to noise. So the ETC had to be able to deal with that in a general way. And the way that we model that is under this unifying concept of what we call observing strategy. So observing strategy is essentially the prescription for how you add together or subtract pixels in your detector to get to a final signal to noise, like a signal to noise on a photometric point, signal to noise on an extracted spectrum, things like that. That's the strategy. We wanted the ETC engine itself to have a stable API supporting different clients, right? And so, when you go on the website and you go to the ETC user interface, that's one client, so that accesses the engine. But there may be other ways that users can interact with the ETC calculations, right? The other way specifically here is that you can download the Python module and run your calculations yourself on your own machine. And so it had to allow that. So again, that's another advantage compared to the Hubble exposure time calculators. Of course, doing all this in 3D and with all these operations, we realized, this is going to be fairly heavy to do. And so it couldn't be so heavy that DTC would not become usable, right? If you had to submit a calculation and it takes an hour to compute, it's not going to be useful as an exposure time calculator. So we do have requirements for this to be relatively fast. I mean, so basically we're talking about seconds is acceptable for an exposure time calculation. But minutes less so. This cannot always be true for every type of calculation you do. Sometimes you set up something that's very complex. A few of the modes are very, very complicated and heavy, so those might take a little longer, and you may have experienced that. But we continue to work on optimizing this to make it really as fast as possible. And then finally, ETC should be template-based. And so we presented this to what was at the time was the JWST advisory committee, which is now become the, this has changed. We now have a JWST user committee, but this was the advisory body at that time. And we presented that to them, and they were happy with it, and they recommended that we released it. So that was in 2016. So it took a few years to develop this until we could reach production. All right. And so this is what the production ETC looks like. And so if you remember the prototype, you can see there's a lot of the heritage in this here. And there's some differences as well. So now we have split things up in a way. So you have calculations. You have scenes and sources, which is your astrophysical scene. There's a tab to upload your own spectra if you don't want to use one of the canned ones. And then there's caveats and limitations, which is basically a bit of documentation. But still, the same thing is that you can pick your instrument, and there's a drop-down menu, and under that there are modes. And so you can calculate, or you can make an HC calculation by that mode just by clicking on it, and you get a list of calculations here. In this case, these are 3 calculations of the same scene. You can modify these calculations on the right-hand side here. So basically, the workflow here is intended to go from left to right, top to bottom. You start from there, you go to the right. So you do your calculation first. All calculations are always done with a default. So it means that you don't have to, like if there were no default, if you couldn't run a calculation just by running it, clicking on a button, you had to guess what an appropriate parameter to fill into it would be. In this case, they're default, so these are valid calculations, so you can at least get some feel for what a valid number will be for filling out. So basically what you do is you do a calculation, and then you can go into the right and click through the menus there and only change the parameters that you want to change. Right? So maybe you're happy with your extraction aperture. The default, you have a point source default is probably a reasonable number, but you want to change your source flux. You don't have to change both, then you only have to do is change your source flux, and you get a reasonable number out. And then at the bottom, there are all the outputs for the calculations. Here you have your 2-dimensional signal-to-noise ratio here. So this is an image of basically on the detector plane. Then there's a plane here called Detector. So that is like a simulated kind of observation, which is in units of a rate, so electrons per second per pixel, and with noise added to it. There's a plane that you can explore saturation, because obviously you can look at every pixel. So some pixels might be saturated, some might not be. Maybe you don't care about certain pixels saturating, others saturating. So you can get a feel for that. And then finally, this is a relatively new addition. This is a groups before saturation. So basically, what that means is how long of an integration can you do before a certain pixel in your scene saturates. And so that is something that decreases the number of iterations you have to do. You don't have to do it by trial and error. You can just go see, I can make 10 groups here in my integration before I saturate. So now I'll go into APT and set it to 9. You don't have to try and see if it saturates or not. And then there are one-dimensional plots to the right. And then finally, there are scalars in this table to the right here. I guess the most important one is the signal-to-noise ratio here. That one. This is also where you find the errors. All right. All right. So you can split out the exposure time calculator software into 4 different pieces. And so there's the 3D ETC engine, which is what we usually, when we talk about Pangaea, we usually talk about the engine. So it was originally a code name that was created for the full project, but the other things are, they're not so public. So the Pangaea part it tends to be the engine. Pangaea, by the way, is a minor Greek goddess who's daughter of Selene, I believe, who was the goddess for the moon, and so Pangaea means all brightness, and so there's a reason we picked that name. All right, so there's the engine, a Python engine to do the calculations. There's a reference database. If you download it, right, it'll be in this folder called Pangaea_data. And so this is the database that contains all the data needed to run an ETC calculation. Throughputs, detector noise parameters, what's the read noise per read, point spread functions, and so on and so on. And so there's a very tight split between these two here, in the sense that the ETC is what we call entirely data-driven. So you could actually set up the exposure time calculator for a completely different observatory just by changing the data here. And so this includes even names of filters and so on and so on. So there's nothing hard-coded in here, or very few things. Then there's the web application, which is what you access when you go to jwst.etc.stci.edu. So it contains the user interface and the collaborative functionality. There's a server behind that handles, how when you save an ETC calculation, it stores that and makes sure that it's accessible when you need it again, and then makes sure that it's accessible to your collaborators. And then finally, but not least, there's the JWST background model. And so this is also available through a tool called JWST_backgrounds. I'll talk a little bit about that, and I think Bill is going to talk a little bit about that later as well. And so I'll talk significantly more now in this presentation about what goes into the background model. But it's a fairly detailed model necessary to use JWST. All right. Whew. How's it going so far? All right. So any exposure time calculator will have to do the sort of the steps that are illustrated here, right? You have to define what your object is that you're looking at in proper astrophysical units. You have to take that, and you have to figure out how much of that signal gets through the telescope system. Nothing is 100% efficient. And so there's some throughput associated with the telescope. In addition to that, the whole observatory may impart a background to that as well. You get not just background from your astrophysical target, you also get background from your telescope itself. And so these are important components. Once the light is collected by your telescope element, you have to go through your primary, secondary, into a pickoff mirror, into the instrument. You have to deal with the throughputs of the instrument as well. Right? So here, for example, this is I believe the MIRI filter wheel. You can see all the different filters, right? So the signal has to go through that, and typically in an instrument, there's also lots of mirrors that bounce the signal around. And again, nothing is 100%, so you have to take that into account. For more complicated instrument modes, if you're an integral field unit, it gets even more complicated. But eventually, you have a signal that has some throughput to it, and that's carved out in some specific way, will reach your detector. And so your detector has an efficiency as well. It's not 100% detecting every photon and converting it into an electron. It's pretty high, but not 100%. And then the detector itself has noise sources. So if you talked about read noise, when you read out the signal, the number of electrons, that measurement is not a perfect measurement. There's noise associated with it, and so the ETC has to calculate that as well. And so at the end of the day, what that gives you is a signal. In the case of James Webb, all signals are in rates, electrons per second, and a noise. Again, because the signal is a rate, the noise has to be a rate as well. And so you divide the two, you get a signal to noise. And hopefully, as you design your observation, your signal to noise will be higher than 5, and then you're happy. For some of us, it has to be even higher than that. Yes. All right. All right. So I'll step through the algorithm here, all the steps and how it actually works within the exposure time calculator. And so on the right-hand side here, you have an illustration of the scene cube, as I talked about before, right? And so again, it has 2 spatial dimensions and 1 wavelength dimension. You can also think of the spatial dimensions here. If it's an image, it's obvious, it's just in arc seconds. If you're interested in spectroscopy, there may be a preferred axis here along which you disperse a spectrum. So you can also think of them dispersion as cross dispersion. So the first thing that the exposure time calculator will do is to take your parameters and create an astrophysical scene. So it's an abstract cube, and it has units of surface brightness, right? And so you have Jansky per square arc second as a function of wavelength. And so it's sampled in some way, and in practice it's oversampling the PSF by some factor. But the sampling in different ways does not change these units here. All right, and the next step here is to sample the scene then in angular and wavelength space here. And so there's a number of considerations for that. For one thing, it's an exposure time calculator. We need to conserve flux. We can't have operations along the way that throw away flux, because then you're not going to get the right result. So if you input a line, a spectral line, for example, if you undersample that line, you're not going to get, when you integrate over the line in the final result, you're not going to get the right result. So the sampling has to resolve the lines. It has to oversample the JWST resolution. In fact, the native detector sampling undersamples, in some cases, the point spread function. For example, NearCam is Nyquist sampled at 2 and 4 micron, depending on the two channels. So if you're using the long wavelength channels, if you go down to 3 micron, it's undersampled. NearSpec is undersampled by quite a lot. And so that's another reason you have a lot of dithers when you observe with JWST, is to also improve the sampling that you have. So if you sample at the native detector resolution with the exposure time calculator, you'll undersample your result and it won't be very accurate. So it subsamples the native detector resolution. You add your sources into the scene here. We'll talk a little bit more about how to add point sources here. But at the end of the day here, you still units of Jansky per square arc second as a function of wavelength. And so at this point here, you have sort of a very idealized scene. If you have an extended source, it might have an extended distribution, but if you have a point source, it's essentially a point. It doesn't know anything about what observatories is going to be observed with. And so that's what's going to happen in the next step. Now we start to tell the scene what observatory is looking at it. And so the first step of doing that is to convolve each wavelength plane with a monochromatic PSF. So again, you think now of the scene cube here, and so you have some sampling here, so you have a number of wavelength planes in this direction here. We can use the WebPSF tool to calculate an PSF for just a single wavelength, essentially for a very narrow filter. And the reason we have to do this is that the point spread function for a diffraction-limited telescope, for any telescope for that matter, but specifically for diffraction-limited telescope, changes significantly with wavelength. Right? You go to longer wavelength, you go to twice the wavelength, right? Your angular resolution decreases by a factor of 2. And so what that means here, if you were to take, you can calculate a PSF through a filter, but the shape of that PSF will depend on the color of your source. That's a way to think about it. What if your source was monochromatic? What if your source had no continuum, had a single line at 4 micron? Then the point spread function you get out, no matter what filter you observe that source in, will be the point spread function for 4 micron. If you have another source that has no continuum, a single line at 2 micron, the point spread function for that through the same filter of those two sources will be different, because one will be the point spread function at 4 micron, one will be a point spread function at 2 micron. And so the PSF shape is color dependent. Now by convolving through the scene cube here with wavelength dependent point spread function, we ensure that no matter what the color of your source is, the point spread function is a reasonably okay model of what comes out in the end. So this is an important part of the ETC. All right, so next step here is that we have to calculate the throughput. So you multiply by the telescope throughput, and in doing that, you can convert to a photon rate. So instead of having a surface brightness, Janskys per square arc second, we now have a number of photons per square arc second per wavelength per micron. And the reason we know this now is we know the collecting area of the telescope is about 25 square meters. And so that allows you to actually count how many photons get captured by that bucket. Then the next step here is to multiply the instrument throughput and the detector quantum efficiency. So what this does is it takes the photons that the telescope has picked up and converts them into electrons. Because electrons is what's actually detected and counted in the detector. So then you get in units of electrons per second, per square arc second, per micron. Okay, you still have a cube. So it's sort of just you've changed units and you've changed the color of it a little bit through all the different throughput curves. Now the sixth step, this is where it gets a little complicated. At this point, we have to, we're not observing a cube, we're observing something that's on a flat detector. And this is a projection. You have to project the cube into a rate image on the detector. And the units of that should be electrons per second per pixel. And so the way to think about this here, so this is illustrated here as well. If you have an image and you're projecting your cube, what you're really doing is you're just integrating the whole cube along the wavelength direction in a straight line. So you're collapsing the cube, you get your image. If you have a spectrum, on the other hand, let's say you have a slit here. Essentially what you're doing is you're integrating along one of the spatial axes. And then do the math, you end up with a dispersed spectrum on your detector. So it's a matter of projecting, but projecting along different directions. And so written out in math, it looks like this here. All right, so you have the imaging projection here. So you have the cube here, so as a rate. It's a function of two spatial dimensions and a wavelength, and all you do is you integrate that. It's a function of wavelength, and you get your image. You can have a spectral projection here. And so in case there's a simplification in here, and you're using a slit, you put a mask in here for the slit, and then you project straight along the axis, along one of the spatial directions. And then you get the dispersed spectrum on the slit. Now, the approximation that's in here is that because you're collapsing along the dispersion direction in the cube, you lose all the spatial information that's within the slit. So in reality, you don't really get, like say, if you're observing a source, you have a wide slit, and say you have a binary in there that's sort of turned a little bit. The spectra that comes out of that slit will be two spectra of the objects, but they'll be offset a little bit here. But because in this approximation here, you've collapsed all that down, you don't get this little offset between the binary within the slit isn't modeled right. They just come out the same way. So that's the approximation there are for slits. So you might see that. So this projection here is used for the near-spec multi-object spectroscopy and the fixed slits, and also for the integral field units for each of the different slices that are in there. Now there is a more exact version of this here, and so that's what we call the slitless projection. And so when you have slitless spectroscopy, right, you can't do this anymore because you don't have a slit anymore, so it means that every pixel encodes both spatial and wavelength information. And in effect, every pixel sees all wavelengths. And in that case, your projection is no longer orthogonal to the axis of your cube. It's along some oblique curve in the cube that depends on your dispersion function. And so that's encoded here in this factor here. And so this is computationally just a lot heavier. So that's the reason we're not using it for all the slits. And it's the reason that when you're using slitless modes, especially if you have a lot of wavelength planes, if you have high spectral dispersion, they tend to get a bit slow. It's in large part because of this projection here. But we have to do it because otherwise we can't model it properly. And so the converse of that is that we're making a little approximation for the slitted spectroscopy, but you get it faster. All right, so what we have now is that we have a rate image on the detector. So all we know now is that we have a detector and we know how many electrons we detect per second per pixel. But we haven't said anything about noise yet. So we have the signal part, we don't have the noise part. So that's the next part here. So we have to calculate the noise part as input for that. A rate is one of the inputs for that. It's not the only input. Rate is an important input because anybody who's done an ETC knows that a big noise component is shot noise, just Poisson noise from the incoming electrons. So that's an important noise part, but there's readout noise as well, for example. So the next step here uses this information with a model of each pixel for how, what its noise properties are, along with shot noise from the electrons, and it creates a noise image. So now you have a signal image and you have a noise image. Noise image, signal image, of course, have the same units, electrons per second per pixel. All right, so now you have your signal to noise as a two-dimensional detector. Again, it's still not quite what you want. Most people will want aperture photometry. They're extracting photometry of a source, and they want to know the signal to noise of that source. Or you're extracting a spectrum as a function of wavelength, you want to know the signal noise on that extracted spectrum. And so the next step here, 8 here, is to extract photometry in one-dimensional spectra. And basically you're doing that because you have the signal to noise in every pixel, you can apply linear noise propagation for this. It's usually an additive process. You add pixels together, you subtract pixels. So you use noise propagation here, that'll give you a signal and a noise of your extracted number. Of course, once you have a final signal to noise ratio, these are dimensionless. And that's it. You celebrate. You're done with your calculation. All right. So let me talk a little bit about the strategies here. So we've sort of very, very briefly talked about how you add numbers together once you have your detector plane in order to get your final signal to noise. So when you see the word strategy, and so this is something you actually see right in the user interface, what that refers to is this formula here. Right? So we assume that you always have a rate in each pixel, and you're doing a sum over that. But the sum may have weights on it. Obviously, these weights can be negative too, like if you're subtracting a background. So you do a sum of these with weights, and you end up with a total extracted signal. And so just regular noise propagation will tell you that the variance on that total signal here is this matrix multiplication here with a covariance matrix. And so this is also where correlated noise comes in. So if the noise in all your pixels is completely independent, this matrix will be diagonal, and you won't have 0 in all the off-diagonal positions. But if you have correlated noise, you can fill these out with values and model correlated noise as well. So this is where that requirement comes in. The weights here, there's an example in the next slide. But the weights basically do is they encapsulate the information in this strategy. All right, so here's an example here for regular aperture photometry here. So here's an output from the ETC. So I've drawn circles on this. The ETC right now does not draw the circles, extraction circles on, although that is in the feature list for future development. But basically what you typically do is you'll sum together the pixels inside some extraction aperture, and then outside of that you have another sort of annulus where you also sum the pixels, and those allow you to measure background, and so you can subtract them. In this case here, there are of course the two sources here, and so you don't want your background to end up and including some of the signal from this, but that's modeled by the exposure time calculator as well. But it's also at the same time something to be careful about if you have a complicated scene. And so you can write out the total flux here, and it's basically it's a sum of the pixels inside the aperture, and you subtract the sort of an average of the pixels outside that you use for background, and you can just rearrange this here, and then you can get a prescription for the weights here, and that's the strategy is incorporated in ETC. And this also makes it easy for us if folks say, well, we want to have a square aperture or some other weird thing. It's easy to do because all you have to do is to write out this formula and figure out what the weights are and implement it that way. So nothing's hard-coded. There's a little note here then in the ETC here. There's a choice for noiseless background. And so what that means is related to this. You can, of course, within the ETC, you can say, well, I don't care about this background here. I mean, in real life, you have to subtract a background, but say, okay, well, what if I just magically know what the background number is, and I don't make a measurement? Just no. And so when you subtract it, this term here doesn't add any noise. So that's what it is. So you can select that within the exposure time calculator. If you select noiseless background, it means that I magically know what my background is. I can subtract it, but this subtraction doesn't add any noise. So it's kind of an idealized situation. So that's what it means. You can see here the selection here. All right. Okay, so similar for spectroscopy here. So you have some examples here of what spectra look like in the output of the exposure time calculator here. I've just taken, I think it's in sort of an extended source. I put an emission line in it somewhere. This is if it's observed with a fixed slit with near spec. In this case, the strategy is that you specify a half height of the extraction aperture, and then there's a background aperture on each side. Here, so you sum all the pixels on each side. You do this for every column and wavelength, and so each column gets a signal to noise, and so you get a signal to noise spectrum. If you use a multi-shutter array, so this is selected to be one where you open 3 shutters, but you keep a shutter closed in between here. So there's 5 shutters along here. You've opened these 3. And the strategy here is use the full shutter extraction. And so it means you sum all the pixels on your source, and you use all these pixels here on each side here to subtract the background. And you can see it's an extended source, so you spill over some of your signal into your background shutters here, and you can use that to check for that as well. All right. Okay. Any questions so far? All right. So those are actually fairly simple strategies. So we have what's called multidealer strategies as well. I've talked a little bit about that. Those are relevant for IFUs and for chronography. And so this is where you're doing one exposure and you're subtracting pixels from another exposure. So for example, for IFUs, there are 2 strategies available. There's one that's called not in scene, and there's one that's called not off scene. The not in scene is what you would typically use if you have a very compact source or a point source that you're observing. And so what the ETC will give you is this here. So what essentially has done is it's taken 2 exposures, but one offset from the other, and you can specify the offset in the user interface, and then have subtracted the 2. So here you have a positive source, and here you have a negative source. And then what the strategy does is it extracts all the pixels, it adds all the pixels here, and it adds all the pixels together here. Of course, there's a minus here, but then it adds both of them together. But there's no background subtraction, because the background subtraction is taken into account when you subtract the 2 nodes. And so the error is propagated through that subtraction as well. If you have an extended source, you might use a not off scene. So what the ETC is doing here is that you have an exposure on your target, and then you have an exposure somewhere else that's just assumed to be empty, except for the background that's otherwise there. Then it subtracts the 2, and you extract just this one here. But once again, the noise that you add to your calculation by having this other field observed is taken into account. All right. So let's talk about the detector noise here and the detector configuration here. So this is often the subject of a lot of confusion because there's a lot of parameters going into this. So you have with JWST, you have a lot of freedom for how you specify how your detector is read out. But the fundamental point of that is that because the reads are non-destructive, right? It's not a CCD. You don't destroy the electrons that you're trying to read out. You can read it as many times as you want, and you can read it while you're exposing. And so you get this what is called a multi-acuum up the ramp read here. And so what you have is here is a signal, and you have a function of time. And what you have here is different reads, different frames. And this, as you're reading, every time you read, you'll get higher and higher signal because the detector is getting signal from the sky. And at some point, you're happy with your exposure, or with the integration, sorry. And you can reset the detector. So all the pixels get reset, means you remove all the electrons, you go back to 0 again, and you can repeat the process. And then the measurement that you're actually getting is the slope of this. That's why the ETC is calculating everything as rates electrons per second, because the measurement is the slope. Right? The steeper the slope is, the brighter your source is. All right, so the added complication to this is that you can group frames together. So each frame is a read, one complete read of the whole detector. Or if you have a subarray, it's a read of the subarray. Right? So basically, what the software of the detector is actually doing is it's stepping through all the pixels in a pattern until it's gone through all of them. And it goes very fast, but it's not an infinitely fast. Then you have a group, which is a set of frames here put together. And what the onboard software does is it averages the signal in this group. And the big reason it's doing that is for data volume reasons. there's a limit to how much data you can download from L2. And so if you were to download for some instruments with a lot of pixels in them, if you were to download every frame, it'll just be too much. So you group them together, you average these out, but you can still get a slope, right? So you get an average here, you get an average here, you get an average here, and you draw the slope between the black points here. All right, an integration is one ramp. It's an integration. It's not the same as an exposure, because an exposure can be, you can have multiple integrations after each other. And so an exposure is a set of integrations, and these get saved in one file as it comes down. In terms of the exposure time calculator, what the difference here is that it assumes that a single exposure doesn't move the telescope. You don't do a dither or anything. You sit on the same part of the sky. And so you can have an exposure, you can dither, you can offset, and then you can do another exposure. So dither is something that moves the telescope. All right. So I use this to try to explain why the noise behaves the way it does with up the ramp reads. And so this is related to this farmer here who has sheep, but he's nearsighted. So he's not that great at counting his sheep. And so what you have here is basically, if this is your pixel here and you have, there's a number of sheep that has come home from, from pasture, and they're coming in. So the farmer wants to know how many sheep he has. So as they're coming in, he's counting them. So he counts these 4 here, but maybe he counts 3 or 2 or whatever. And then he waits a little bit of time, and then you have more sheep coming in, and he counts them again. And he counts these, and he still has plus minus 1 sheep counting error here. The thing is that he counts the new sheep. This is the first time he counts the new sheep. But the old sheep, the ones who are already there, he counts again. And so it counts as he actually measures the first sheep twice now. The new sheep that came in, he has only measured once. And so it means that you can't calculate the noise here as if the first sheep that came in are new. They're correlated. And so he can do this again, and more sheep comes in. In this case, the first sheep that came in, now he's counted them 3 times. The second ones he's counted twice, and the last ones he's only counted once. And so what that essentially means is, because the read is non-destructive, you count the first sheep many times. He actually, when you average out over the sheep, he decreases his counting error, because he has more chance to count some of them. And so it means that the more reads you have, the more frames you have in your integration, the lower your read noise is. And that's why you want a lot of integrations. The read noise, the read noise can actually drop faster than your Poisson noise if you're in the regime where you still don't have a lot of frames. And so this is the actual noise formula that goes into calculating the variance on a single pixel of an up the ramp read, where M here is, you don't have to write this down, this is available, but M is a number of frames per group, right? So that's your readout pattern, and N is the number of groups per integration. And you can just inspect it over here. So this is the readout noise here. This is the variance. And you can see that the readout noise decreases roughly as the product of frames times the number of groups. So it's number of frames per integration, M times N. So the longer the integration is, the lower your read noise is. And it goes pretty fast in the beginning. And so if you use the exposure time calculator and you plot your signal to noise as a function of time for a single integration, you just make the integration longer and longer with more and more groups, you will see your signal to noise increase. It can happen, right? You can see your signal to noise increase faster than the square root of time, as you might be used to. And it's because of this effect here. So don't be surprised when you see this is a real effect. All right. See how much time? I have a little bit of time. Okay, so I just wanted to talk a little bit about the different times that are available. So this is something that's it comes out of the ETC at the end here. There's something that's called exposure duty cycle here, and so what that is related to is these different definitions of time. Now, I told you that we have a detector that gets read out 1 pixel at a time as you go through it. So you can define a time as a time from, say, you're reading the first pixel until you're reading the last pixel. You can define a time, for your whole integration and for your whole exposure that's defined as the time, when you just start reading the first pixel until you've just done reading the last pixel. So that's different than if you define your time as something that's seen by a single pixel. I imagine just a single pixel, you don't know about all the other pixels. Your time will be different from the time that you first read to the time you last read it. Now, the last time, which is called, so the first time is called an array-based time, and the second kind of time is called a pixel-based time. The array-based time, of course, is important for how long it actually takes to do it. The pixel-based time is more important for, like, for example, calculating saturation. Right? So a pixel only cares about being saturated in the time it's actually seeing photons that are downloaded to the ground. It doesn't care about all the other, if some other pixel is doing something later on. If it saturates at that point, it doesn't matter anymore. So the exposure time is the array-based time that the detector is operating during a single exposure command. The measurement time is a pixel-based time, which is the interval between the first and the last measurements of a pixel. Right? And so if you're thinking of, how many electrons, so people sometimes ask, how many electrons do I have at the end? Because you're measuring rates, and we don't really care. Well, but the measurement time is the one that's relevant for that, like if you're thinking in CCD terms. And then there's saturation time, which is just pixel-based time interval from the reset of a pixel to the final read of that pixel in an integration. And then finally, we can define something that's the exposure duty cycle, which is the pixel-based measurement time, right? So the time that you're actually collecting useful science photons, divided by the array-based exposure time. Right, so the latter is longer than the first, and so this is kind of an efficiency that's encoded in the readout pattern. And so the ETC engine will makes that available to you. And so this gets more and more efficient the longer your integrations are. In the ETC, so this is about saturation here, so it's also related to the integrations. There are 2 different kinds of saturation that's dealt with in the exposure time calculator. That's what we call partial saturation and full saturation. The partial saturation is if the integration saturates before it completes, but where you have recorded more than a minimum number of groups that are unsaturated. So it's the same kind of thing, or you can have a cosmic ray hit or whatever. If something bad happens to your integration late in the game, it's okay because you still have a measurement in the first part that's not lost. And so you can saturate your integration as long as you have enough to make a slope measurement in the first part of it. Now, full saturation, that is if saturation happens at less than the minimum number of groups, right? So you can think of the minimum number of groups as 2 groups, right? If you have less than 2 groups, you don't have a slope anymore. Now for the MIRI detector, for various other reasons, the minimum number of groups is long, it's 5, and that's related to that detector. So the ETC displays those 2 types of saturation in the user interface here. And so the value of the saturation map can be 0, 1, or 2. So 0 is not saturated, 1 is the partial saturation, and 2 is the full saturation. And then the take-home is just if you have full saturation, you lose the data there. If you have partial saturation, you can still use it, but you don't get benefits from going longer on something that's partially saturated because you don't improve your signal to noise at that point anymore. All right. Okay, so what this slide does here is basically summarizes a lot of what we've talked about here. So selecting the optimal combination of readout pattern, number of groups, number of integrations, and number of exposures is a trade-off between all these different things. More frames decreases read noise. Shorter groups increases data volume. Longer groups increases the chance of a cosmic ray hit during the group. So you lose more data there. Shorter groups, longer integrations make cosmic ray corrections better, and so on. And then there's more. Yeah, so I didn't really talk about this here, but I think I'll skip over that for now, in the interest of time. Okay. So that's a basic algorithm from the ETC here. Now, I talked a little bit about earlier here about the reference database for the ETC. So we're switching gears. All right, so I just wanted to show you the structure of the reference database here, because some people like to, pull some of the instrument information out of the ETC, and this is a chance for doing that here. So it's all, when you download it, it's all organized according to instrument, telescope, and what's available are things like throughputs, dispersions for dispersive elements, or spectrometers, the various filters, detector QE, and the point spread functions. And just to show what it looks like, for example, here's an example from the PSF library. Right now, it contains almost 5,000 individual monochromatic PSFs, and it's a subsampled by an integer factor of pixel size. And you can see here, this is for the near-cam short wavelength PSF as a function of wavelengths from like about 1 micron, right, to 5 micron. Actually, I think the wavelength range is to 2.5 micron, not 5 micron, because it's only short wavelengths. All right. Switching gears again. There's some notes to say about when you create your astrophysical scene. The take-home here is that there are two different entities when you create your scene. There are sources and there are scenes. And both are unique in the sense that you can define a source, so it's an individual object in the sky. That source can appear in different scenes, that same source, even though, so you might have a certain star that you like, and but you can put other sources around it to create a completely different scene, but the source by the ETC is still considered the same source. So if you change the source in one scene, it changes in another. Source is defined as a spectrum with a continuum, a normalization, and some lines, and then it has a shape. Shape can be point source or extended, or there's a number of extended sources you can choose from. And then a scene, what that basically is a list of sources, and that's it. Each source here has a position in the scene, so an X or Y offset, and an orientation. Like if you have a galaxy, for example, with a major and a minor axis, you can rotate it. Right, as I said, the same source can exist in multiple scenes. Just wanted to make a point about how point sources are placed in the scene. And so this is important for things like if you're using a narrow slit, like the multi-shutter array, the ETC will correctly calculate where the source is within that shutter, even though the placement is at some fraction of a pixel. And the way that it does that is that, let's say, if you have a point source here and you have your sampling grid, and you have a source here, you might be tempted to just place it in this pixel here, but you can see the centroid of that won't be right. So the way it's done is that you subdivide the signal into 4 different pixels. And so that these 4 pixels together has the correct centroid. And then when you convolve it with the PSF, now remember the PSF is much bigger than this is subsampled. When you convolve with the PSF, the centroid of that PSF is actually right. And so you can, at least, to within approximation is right. Another way that it does, deal with sampling issues is for extended sources. So this is just something I just drew up here, but it's not a real profile. But for galaxies, people who do that, and you use a Sersic profile, you know that you can have parameters where the core of the galaxy is very small compared to the wings, and this core may be completely undersampled by the sampling of the ETC. So here we take steps to ensure that when you integrate such a curve over an ETC, that it is actually correctly flux conserving. We had issues with that in the beginning of some time ago, and so that was fixed, so that they can deal with say galaxy profiles with very small cores. All right. Okay. So we're now getting to the background here. So this is another important thing. So I want to make sure that we get through this in the time we have. So the JWST background model here, it uses a dynamic background model. It's called the background model generator, or the BMG. And so this is a background model that has 4 different components to it. It has galactic, interstellar medium plus stars, and so this says stars, so something is actually smoothed out. So it doesn't, the background model doesn't see individual stars. It has much, much lower spatial resolution, but still you get like a background from the galaxy itself. You have a component from zodiacal light. Zodiacal light is both position and time dependent in the L2 orbit. Then there's out of field stray light. And so what that basically is that, I mean, you don't have a baffle on James Webb. And so it means that it sits somewhere in L2, it points in a certain direction, and you have sources, you have astrophysical sources all over the place. And so those shine on the observatory, and they might scatter into the sightline. And so that's out of field stray light. And then there's thermal emission from the telescope itself. So once you go to wavelengths longer than, I don't know, 14, 15 micron or something like that, JWST is limited by its own thermal emission background. And so there are 2 ways to use the background in the ETC here for this, especially because it's zodiacal light, which is time dependent. You can use a dated background. So if you have a pointing and a date, you can calculate what the background will be at that date. But we realize in many cases, of course, you don't know what date you're going to be observed. So you can also calculate a dateless background, which will, and you can choose low, medium, or high, which is the 10th, the 50th, or the 90th percentile of the background range over a full year on that date. On that pointing. All right. So the thermal emission. The SODI and the ISM, they're heritage from Spitzer systems. Maybe that you can answers your question as well. And so it was actually delivered to us from IPAC. The thermal self-emission, basically you can look at it. There's a model for that is, and you can compare that to the requirements of James Webb. But you can see the thermal background, how it increases rapidly here over many orders of magnitude as you go beyond 10 micron. So the stray light, so this is the out of field stray light. It is underlying this is a fairly complicated model that includes astrophysical sources, as well as a efficiency function of the telescope itself. So the efficiency function says something about where, what part of the sky, if you're looking in this direction here, what part of the sky gets a lot of light scattered from. So depending on where the telescope is looking, what ends up in that part of the sky that might scatter a lot, that gets included in it. And so this is this big pre-calculated database that gets looked up given a pointing in the sky. You can access the backgrounds using the JWST _backgrounds tool, which is a little Python script, and so that will plot all the different components of the background model, and it'll also give you these what we call bathtub curves, which is a background as a function of time within the visibility window for that given pointing. And so if you're very background sensitive, you can use this to plan your observation. And I think Bill will talk more about this. All right, cosmic rays are taken into account in the ETC, but in a very statistical way. So we don't calculate individual hits, but we calculate what the rate is. And then given the rate, we'll know how many pixels are affected. And then basically what we do is we subtract some of the exposure time based on how many pixels are affected. And we make a very conservative estimate that half of the ramp on average is lost per cosmic ray hit. This is conservative because when the pipeline actually corrects for cosmic rays, it'll be a bit better than that. We also assume that a number of pixels will be affected by each cosmic ray. So in practice, what happens with this is that you start to get significant effects from cosmic rays if you have integrations that are longer than about 1,000 seconds. If you're shorter than that, you're all right. All right, target acquisition. So target acquisition is done in a quite different way in the ETC, and that's because of the algorithm that is used to acquire targets on orbit. So it does a lot of calculations on the telescope in order to do the target acquisition, because you don't have, if you acquire a target, you don't have time to download the data and look at them. And so what it does is, if you have your ramp here, it actually takes the first group, the middle group, and the last group. Then it takes the difference between the middle group and the first group, a difference between the last group and the middle group, and then it takes a median between the two, and this is sort of to get rid of cosmic rays. And then it throws away all the other data. So the ETC, when you do a target acquisition calculation, it uses this algorithm here, and that's why you find generally that your signal to noise in the target acquisition is less than what you'd get with the corresponding imaging mode. So in case you compare the two and wonder about that. Yeah, let me just skip that. All right, how do we know the exposure time calculator is correct? Well, we went through a long exercise in ETC a couple of years ago with all the instrument teams who they have all calculated. They made their own exposure time calculator, sensitivity calculations for their instruments. And so we took those and we compared them, we benchmarked them to the ETC calculations, and we required that at least 90% of the calculations were closer than 10% in signal-to-noise ratio. In many cases, we were much better than that. In some cases, we were close to that. Often, this is comparing our 3D calculation to what was a one-dimensional calculation by the instrument team. So we wouldn't expect, exactly the same result. But basically, all the modes were checked out this way, and for all the filters and so on. So we're pretty confident. Like, given the assumptions, of course, once you're in orbit, things can happen to, the throughput wasn't what we thought it was or whatever. But given the assumptions, we think the calculations are mathematically good. How to use the ETC with APT? Just really briefly, the workflow, of course, is that you create your scene in the ETC and you do your exploration there to figure out what your exposure parameters should be or what you want. And we have taken some effort with the ETC to make sure that the labels here are the same, they match what you have in APT, so that once you have decided number of groups, number of integrations, readout pattern, and so on, that you can take those and put them directly into APT, and it should be clear, which value goes where. All right. I had some examples here. I'll skip over them sort of relatively quick here, but just to show what some real life calculations from the ETC might look like. Here I can have, for example, a fairly complicated galaxy. Put in some extended sources, some point sources with different colors. You can see the NearCam image here, so I just made some, an RGB image in DS9 to show the color differences. You go to mirror, you have some very red sources up here with noise and so on. So if you like this kind of color images, you can do that. And then you can take the same scene, put a slit on it, in this case, MIRI, LRS, and MSA, and then, this is where the slit goes, and this is what the output for the spectroscopic modes look like for the same scene. All right. The ETC is a web application, so it has a collaborative work environment. Essentially, what it means is that, and you think you did this in your homework as well. Once you have done a calculation here, you can share it with your collaborators, and you can grant them permissions. And we ensure that your workbooks are there forever, or at least for as long as you need them, hopefully. One thing to be said about this is that ETC is updated from time to time, and so the way we ensure that your workbooks are backwards compatible is that if there's a new version, it's flagged as read-only, your workbook, and all you have to do is to copy it, and it will do a calculation with the new version of the ETC. As I said, the ETC engine is available as a Python module. And you can find it on PyPy here, and you can pip install it, and there's on JDocs, there are descriptions of how to do that. one potential use case for the engine is that it gives you access to all the throughputs that DTC uses. There's a little script here for how to do that within the engine. So you can just pick your instrument, your instrument configuration, and it'll put out as a function of wavelength, the PCE, which is the photon to electron conversion efficiency. And there's some example of this here from MIRI MRS, what they look like. All right, so this is the last summary slide here. Just some very brief recommendations for how to use the ETC. And of course, there are many parameters affecting it. It's a very versatile tool. It has a lot of power. But we realize that there's a learning curve for using it. And so just some things here when you're doing a calculation. Think about your background subtraction strategy. It does change things significantly. Think about what extraction aperture is optimal for you, whether you have points or extended sources. Think about whether your background is correct for your target, right? And so that's a function of pointing and time. So check that your extraction aperture doesn't contain contaminating flux for other sources. And think about your selected readout pattern, whether it indeed gives you the best signal-to-noise ratio.